What specific problem does FreeAugment aim to solve in the context of data augmentation pipelines, and how does it differentiate itself from previous methods?
FreeAugment aims to solve the problem of optimizing data augmentation pipelines by jointly learning the 4 degrees of freedom, DOF, the number of sequential transformations, policy depth, their types, order, and magnitudes. Unlike previous methods that either limit the policy depth to 2 transformations or rely on myopic strategies, FreeAugment is the first fully differentiable method that allows for global optimization across all DOF in an end-to-end manner using gradient descent. It introduces a learnable probability distribution over the policy depth, ensuring that transformations are not repeated, and optimizes the distributions over types and order of transformations as a unified learning problem. Additionally, it samples stochastic magnitudes for each augmentation from a parameterized distribution, which is learned through backpropagation. This comprehensive approach leads to state-of-the-art performance on various benchmarks, showcasing its robustness and effectiveness compared to earlier data augmentation search methods.
How does FreeAugment work? Illustrate step-by-step the process, including how it selects the number of transformations, their types, order, and magnitudes.
FreeAugment operates through a fully differentiable framework that optimizes data augmentation policies by jointly learning 4 degrees of freedom, DOF, policy depth, transformation types, order, and magnitudes. First, it induces a learnable probability distribution over the policy depth, allowing it to dynamically select the number of sequential transformations applied to an image. Next, it learns the types and order of transformations by formulating the selection as a matching problem, utilizing a double stochastic matrix to ensure that transformations are not repeated across layers. For magnitudes, FreeAugment samples from a uniform distribution defined by learnable lower and upper bounds, which are optimized through backpropagation. Finally, the entire process is optimized using a bi-level optimization approach, where the augmentation policy is refined based on its performance on a validation set, ensuring that the selected transformations enhance the model's generalization capabilities.
Can you provide a simple example to demonstrate the inner workings of FreeAugment, detailing how a single image is processed through various transformations in the algorithm?
FreeAugment processes a single image by applying a sequence of transformations, which are determined through a learned probabilistic model. For instance, consider an image, X, that undergoes a series of transformations, tau_1, tau_2, L dots, tau_k, with corresponding magnitudes, M_1, M_2, L dots, M_k. The algorithm first samples a policy depth, K, from a learnable distribution, allowing for a variable number of transformations to be applied. Each transformation type is selected from a predefined set, ensuring that no transformation is repeated across the layers by learning a probability distribution over permutations. Finally, the magnitudes for each transformation are sampled from learned uniform ranges, which dictate the intensity of each transformation, resulting in an augmented image, tau_kx m_k, for each layer, k. This end-to-end differentiable process allows FreeAugment to optimize the augmentation policy effectively through gradient descent.
What are the theoretical or practical benefits of using FreeAugment compared to existing data augmentation methods?
FreeAugment offers several theoretical and practical benefits over existing data augmentation methods. Firstly, it is the first fully differentiable data augmentation search, DOS, method that jointly optimizes all 4 degrees of freedom, DOF, policy depth, transformation types, order, and magnitudes, using gradient descent, which enhances the flexibility and effectiveness of the augmentation policies. Secondly, FreeAugment avoids the redundancy of applying the same transformation multiple times by formalizing the search over types and order as learning a probability distribution over permutations, thus ensuring a more diverse set of transformations. Additionally, it achieves state-of-the-art performance on various benchmarks, including natural images and other domains, demonstrating its robustness and generalizability across different tasks. Finally, the method's end-to-end optimization approach eliminates the need for complementary heuristics or greedy strategies, streamlining the augmentation process and making it more efficient compared to previous methods that often limit the number of transformations or rely on less effective sampling strategies.
How was FreeAugment validated in the experiments? Discuss the datasets used, evaluation metrics, and the overall experimental design.
FreeAugment was validated through a comprehensive experimental design that involved evaluating its performance on 3 standard natural image benchmarks, 10, 100, and -100 datasets, as well as a diverse dataset comprising 6 distinct domains, including real images, quick draw, infographics, sketches, paintings, and clip art, totaling approximately 0.6 million images across 345 categories. The evaluation metrics focused on top 1 test accuracy, which was averaged over 5 runs with different random seeds to ensure reliability, with a 95% confidence interval reported. The search phase for augmentation policies was conducted on reduced subsets of the data, with a balanced 50% to 50% train validation split, and the search was performed for 300 epochs using specific batch sizes tailored to each dataset. During the evaluation phase, the same training configurations as previous works were replicated to ensure fair comparison, with consistent settings for the number of sync-Hern iterations and temperature for gumball-based distributions. This rigorous approach highlighted FreeAugment's robustness and effectiveness across various domains and benchmarks.
What specific results were achieved with FreeAugment in comparison to other data augmentation methods on the benchmarks?
FreeAugment demonstrated state-of-the-art performance on various benchmarks, achieving comparable or superior results to existing data augmentation methods on natural image datasets 10 100ths and -100. Additionally, it excelled in diverse domains, including sketches, paintings, drawings, clip arts, and infographics, as indicated in the experimental results. The framework's ability to jointly optimize all 4 degrees of freedom, policy depth, type, order, and magnitudes, contributed significantly to its effectiveness. The paper highlights that FreeAugment outperformed previous methods, which typically limited the number of sequential transformations to 2, or relied on less efficient sampling strategies. Overall, the extensive experimentation showcased FreeAugment's robustness and generalizability across different domains, reinforcing its advantages over traditional augmentation techniques.